All right, here we go. So getting going with lecture 3 today. So as I told you, these first two introductory lectures are going to be focused on statistics. And in the last class, we talked about, methods for being able to describe data. But today's lecture, I think, is really, one of the most important lectures of the course, because today we're going to be introducing the concept of why we need statistics, why, rather than just being able to describe data and the central tendency and the variance, the dispersion, that sort of thing. Today, we're really going to try to understand what it is that what the problem is that statistics is trying to solve. And that problem is that what we're trying to do is make inferences about a population using a sample from that population. Okay, and so today we're going to talk about sampling, the process of sampling. We're going to talk about sampling from populations. And when we do that, we're going to talk about quantifying the uncertainty that's associated with that sampling. And so to do that, I want to go back to our human height sample. And I'm going to try and illustrate this on the board by sharing my iPad here. All right. So our goal as statisticians, as geneticists, is to be able to estimate characteristics of a population based on a sample from that population. So let's define our goal as estimating properties or characteristics, and we'll define those in this case as parameters of a population using a sample from that population, okay? And so we tried to do this in our little experiment that we've done this week. And so the question here, or an example of this would be, if we wanted to ask what is the typical height, and when we talk about a typical value from a population, we might talk about the central tendency. So for example, the mean of a student at NYU. That's our goal. And so the reality that we are faced with is that we have a population of students at NYU. And let's define that population as being within this circle. And let's say that that the total population size of NYU students is 21,638 students. And so this defines our population. And the goal that we have today is we want to be able to say, well, what's the typical height of a student in that population of 21,638 individuals? Well, what is the average height? And to do that, what would be the ideal way to be able to do that? To determine with certainty what that average height is in that population. Who can give me an answer? Mark.
You would take all the students, the entire population, and calculate the average from that.
Right.
The average height.
So Mark is going to go and he's going to get out his tape measure and he's going to measure 21,638 individuals' height. And then he's going to use the formula that he wrote down in the quiz today. and he's going to determine with certainty the average height of an NYU student, okay? And Mark's able to do that because he has infinite resources and infinite time, and so that's a feasible thing to do. But in reality, most of us are, have less time on our hands, have less resources, and so we're not able to do that. And so the approach that we take instead is we're going to take a random sample from this population. And when we do that, we're going to randomly select individuals here, and let's just denote them with little marks here. And this is exactly what we did this week. We took a random sample from this population of how many individuals? Does anyone recall? To go back and look at my spreadsheet. How many people filled out our survey this week? I'm going to have to go and check. Or if someone can check for me.
59.
59. Okay, great. So n equals 59. So we took a random survey of 59 individuals from the total population of 21,638 individuals. And the point is that those individuals were randomly selected, and that's one sample that we took from the population. But we could go back and we could take a new sample from that population, and it would be a different set of individuals. So those individuals are randomly chosen from the population. So let's just define some terms here. Let's define the population. And the population is all the individuals of interest. And from that population, we're going to take a sample, and the sample is a subset of, let's call them units. So we are taken from the population. And then the process route that we're going to undertake is one that is known as estimation. So this is the process of inferring an unknown quantity of a population using the sample data. So this, we just want to have some very clearly defined terminology here. And then let's also just talk about that process. Of taking a random sample. What does that actually, what does that mean? If our sample was random, in practice, what is that going to mean? To have a truly random sample.
Everyone has an equal chance of being picked.
Right, so every unit has an equal chance of being selected. And what else? What's another property of a random sample?
Is it no biases?
There's no biases, which means that that the selection of the units is independent. There's no relationship between the selection of the units. Let's say that. Now, what do you think of our sample? Where our goal is to determine the average height of an NYU student from our population of 21,638 individuals. We took a sample of 59 individuals from that population. Who thinks we've taken a good sample? Okay, can we do a thumbs up if it's a good sample? Thumbs down if it's if there's some problems with this sample? I see some thumbs down. Okay. What don't you like about this sample?
Only individuals from the biostatistics course.
Yeah, what's wrong with that?
Not every unit has an equal chance of being selected.
Right, okay. That's true, but you know, so what might be a concern? I guess one concern might be that, you know, there's some relationship between those individuals who are interested in genetics and biostatistics, and they tend to be abnormally large, tall people, right? That is a possibility. And so our sample was biased in some way. I have another suggestion that it doesn't represent the overall population. That's right. We have lots of colleagues, fellow students who are actors and dancers. You know, maybe they tend to be shorter on average. And so our sample isn't perfect, and that's something we always want to consider, is whether our sample is biased. But it's good enough for government work, as they say. And so that's all we've got at the moment. Let's deal with that, okay? So there's this idea that we have the population and we're taking a sample from the population. And this is really a key concept to be aware of. And I want to distinguish the way we talk about a population versus a sample. Okay, so one, we learned about, we discussed being able to visualize data. And so we can visualize the distribution of heights in our population. And so we can use what we talked about in the last class, which is we can plot height on the x-axis, and we have variation in height along the population. We want to convey that. And we can make a histogram where we have all individuals. And one thing that we can do is we can smooth that histogram so that it looks more like this. Okay, when we smooth out these bumps. But we have bins here of individuals of different heights, and we're counting them up. But in this case, when we're talking about a population where we have n equals 21,638, we typically, in a population, we'd like to talk about not the frequency, so the absolute count of each individual, but we talk about the proportion of individuals. And so we can put the proportion on the y-axis here. And when we do this, this proportion sums up to 1. It's a probability density. So this is literally a what we refer to this as is a probability distribution, because it defines the probability if we take a sample from of the probability of finding individuals with a particular height in the population. Okay, and so the key point here is that when in the terminology we're going to use, we're going to say that height is a random variable. And that is, it's a variable that we draw from this population if we randomly sample it, with probability defined by this probability distribution. By contrast, when we take our sample of individuals, and here I'm going to, let's simplify this by saying, let's just say we only have 17 individuals in our sample. Okay. Again, we have height on the x-axis, and here we're going to count the frequency of each individual. That says frequency. And in this case, we would have 2, 4, 6, 8, and we would have a histogram that looks a bit more like this, where we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 individuals that are counted in here, okay? And so this version of the histogram we call a frequency distribution. Okay, so there's two different ways of drawing a histogram. When we're drawing a histogram of a population, we talk about a probability distribution. When we're drawing a histogram from a sample, we talk about a frequency distribution. Now, in both cases, we can compute parameters of these distributions. And so what are those parameters? Well, we talked about in the last class is the mean. So we can define the population mean. And in this case, we'll use the symbol mu, the Greek symbol mu, which we write as this funny U shape. When we take a sample from this frequency distribution, we calculate the mean. We're going to call that our sample mean. And in that case, we're going to use the Roman letter Y, and we're going to call it Y bar. So this is our population mean, and this is our sample mean. We can compute the variance as an estimate of the dispersion. And so for our population, we can compute the population variance, which we learned about, covered in the last class. That's the average of the squared difference of each value from the mean. And in this case, we're going to use the Greek symbol sigma, and recall it's squared because it's the average of the squared differences. For the sample, we're going to use the Roman letter S squared, and we'll call this the sample variance. And then to put it into units that we like, we just take the square root of that. So we have sigma, which is our population standard deviation. And we have S, which is our sample standard deviation. All right, so there's some conventions here that we want to use. So the convention is that the population parameters get Greek symbols, whereas the sample estimates, so they're estimates of our population parameters, is the key distinction here. We use Roman letters. All right, and these are the conventions, and this is the terminology that we want to use for these two scenarios in which we're talking about either the population or the sample. Now, the reality is, typically we don't know the population parameters, right? We're not going to BMark and go out and measure every single individual and determine with certainty those population parameters. And the reality is often populations are infinite in size, or it's unclear how big they are, but they're enormous. So we don't have the resources or the capacity or the time to be able to go and measure them. And even if we did, we wouldn't really know where to stop. Okay, and so that is why we're going to take estimates and use those, take samples and use those samples to estimate the parameters from the population. All right, so let's, if we go back to our example, so we took a sample from, what did we say, 58 individuals? 59. Okay, and just say we've taken a random sample, and who was able to calculate the mean from that sample in the last class? I'm gonna have to go and, does anyone recall what it was? 166.3. So in that case, we're going to use this symbol here, y bar, and we're going to say y bar equals 166.3 centimeters is our sample average from our 59 individuals. All right. Now, let's say we were so inclined to go out into the NYU student population and take another random sample of 59 individuals. And compute the mean of that sample. Let's get a thumbs up if you think that it's very likely that our sample mean will be 166.3. I see no thumbs up. Who thinks it's going to be something different to 166.3? Some thumbs up. All right. What might be a reasonable value that one might get if we did this again?
168.
Now we're going to get a 168 centimeters. Do it again. So we're using a different 59 individuals. Okay. You're 168, but we have Yoni, so I'm going to use y bar subscript y. Thinks 160 would be reasonable. Angela Chiani thinks it might be 170. Christine is saying it might be 150. Okay, so we have a whole bunch of possibilities. And Jay Kaufman is giving us a variety of possibilities. And so that may also be the case. Okay. So the point is that every time we do it with a different 59 individuals, we're going to get a different sample mean. Oh, that's interesting. Okay. Now, here we have, what do we have 1, 2, 3, 4, 5 different sample means. Now just say we didn't really have much else to do. There's not much else going on. And we went and we did it 10,000 times. We did this process of just going in, randomly sampling the NYU student population, 59 individuals, and measuring their heights and measuring their, quantifying the average height, okay? If we did it, let's say we did this 10,000 times. Then we're gonna get a table of, sample means with some value. So let's choose our 166.3, which is right here. And that's going to occur with some frequency. Say that occurs, well, let's make it just 166 to make it a little less precise. Let's say that occurs 100 times. and we do it again, and we get a mean of 165, and we get that maybe 80 times, and 164, and that maybe happens 60 times, and we get 168, and maybe that happens 120 times, and 170, and that happens 140 times, and 180, that happens 120 times, 190, that happens maybe 100 times. And so we're engaged in this, rather tiresome project of going out and randomly sampling the population, computing the mean, and doing it again and again and again. And then what we get is the sample means, each of the sample means that we've computed, our y bars here, and the number of times that we observe it. And so if we have now a set of values and their frequencies, what would we like to do with those to visualize them? We can plot a histogram, just as we did with our data, right? So now we can plot a really special type of histogram where on our x-axis, we have sample mean. We can do this an infinite number of times, so we can consider this to be a population of sample means. So we can have proportion on the y-axis, and we're going to get a distribution of sample means. Okay, that's going to look like this. And this is a very important distribution that we call the sampling distribution of means for n equals 59, a sample of 59 individuals. And so just as with our population distribution up here, now we have a population distribution, but it's a distribution of sample means. And this defines the probability of getting a particular sample mean when we take a sample of 59 individuals from this population. Okay, so this is a probability distribution. And here's the interesting concept, is that up here we said that our height is a random variable. When we're looking at this distribution, the key point is that the sample mean is a random variable drawn from this distribution. But here's the catch. The catch is we never get to see this distribution. Okay, this is not a distribution unless we're Mark, and we've done this crazy project that Mark's embarked on. We're never going to see this distribution, but it exists, inaccessible to us, except through the magic of computers, and that's what we're going to use today. Okay, so and the key point here also is that the sample mean is a random variable, and this is unlike the population mean, unlike mu from our population, which is a constant. All right, so Jay Kaufman, your question is correct. This is the sampling distribution. This is the sampling distribution of means. Okay. Has anyone ever encountered the sampling distribution of means before? It's kind of an abstract concept, and that's hard to wrap your head around, but that's where computing and computing simulation is so valuable. We can actually pretend to be Mark for a day. Inside our computer, we can simulate doing Mark's crazy experiment of randomly sampling a population and looking at what the mean is, and then we can actually plot this sampling distribution of means, and that's what we'll do. But here's the question. So, and since we have a bit of time, I'm going to make some breakout rooms, and we can go and discuss this in our breakout rooms. So let's make breakout rooms. All right, so perhaps this is a better way of being able to motivate the question. But when I dropped in, it sounded like many of you were thinking about this carefully. So here's the question, right? So we take this sample mean from the population, and we want to be able to quantify the uncertainty of our estimate. And this is what we're really concerned with as statisticians. We now know that the answer is not 166.3. We know that that's an estimate of the true population mean, and we want to be able to estimate the uncertainty that's associated with that estimate. Okay. And so the question then is, what are things, and this is the question that I asked you to address, what are things that you might expect will affect the uncertainty? The key things. So who can report back from one of their groups on one of the factors that's going to impact the uncertainty of your estimation?
The intrinsic variability of the underlying data.
Right, the variability of the data, right? So that is, one is the variance in the population. Variance, so the more spread in your population, do you think you're going to have more uncertainty or less uncertainty?
Is that the same thing as accounting for extreme outliers?
Yes, so if you have extreme outliers, then when you do that calculation of variance, taking that outlier, subtracting the mean, squaring it, putting that in part of your variance equation, that's going to increase your variance. So what are those values going to do to your ability to be able to estimate the true population parameter?
Decrease our ability to do so.
Right, so it's going to make it harder to get an accurate measurement. And in fact, let's just say we can write that in a, we can say that our uncertainty is going to be proportional to, do you know that symbol? Proportional to the variance, okay? So that means more variance in our population, more uncertainty, okay? And what's the other factor that's going to impact our ability to accurately estimate the true population parameter?
The sample size.
The sample size. So with a larger sample, what's going to happen?
Less variation.
less
First-
variation in our sample, which is going to result in what? Are we going to
Less
be more certain
uncertainty.
about our estimate or less certain?
More.
More certain, right. Okay, so in this case, we'd say that uncertainty is going to be inversely related to the sample size. So that's 1 over n is when it's the inverse, right? And so we can put these together and we can say, well, therefore, our uncertainty associated with our estimate is going to be proportional to the variance and inversely proportional to the sample size. We can combine those. And so let's consider that metric. So if we take our variance divided by the sample size, that's going to be a way that we can compute the uncertainty associated with our estimate. So this is our sample size. And this is our, sorry. Got to tell me if I'm saying something that doesn't make sense. That's part of that was done by design. This is our sample variance, right? This is our sample size. And then if we calculated this, so sample variance divided by sample size, what are the units going to be for height? Height measured in centimeters. So the units are going to be
centimeters squared over people.
Yeah, centimeters squared over people. And n, we can ignore, n is just generic, so it's 59 in this case, but it's going to be 79. It's going to be our sample variance. So it'll be centimeters squared. So we solved that problem last time by taking the square root of this, right? So if we take the square root of s squared over n, then that's going to be s over the square root of n. And this value is called the standard error of our sample mean, which is the standard deviation of the sample divided by n. So when we, as statisticians, are going to report our estimate of the population mean from the sample, what we're going to say is we're going to say that we have an estimate of 166.3 centimeters plus or minus. We're going to measure the standard deviation of the population. I'm going to have to make it up in this case because I don't have it at hand. So let's say that it's something like, okay, I'm going to make this easy for myself by doing the following. I'm going to pretend that our sample is actually 64, because the square root of 64 is what?
8.
8. So that's going to work out nicely. And let me put 16 up here. Okay, so now we could say 166.3 plus or minus 16 divided by 8, which is going to be 2. Okay, and this is the appropriate way to be able to say what our sample mean and the associated uncertainty is. Avni.
Sorry, I missed what SE stands for.
What, sorry?
What
SE?
the SE, yeah.
Yeah, this is the standard error of the mean. Now, if we go back to our sampling distribution of the means, there are some interesting properties of it. So again, I told you this is a distribution we're never going to see ourselves, but we can simulate it in the computer. And when we do that, what we'll find is something interesting, that this sampling, this is a distribution of means that we would get if we took a sample of n equals 59 multiple times. And the mean of this distribution we can define. And who knows what that mean is going to correspond to? It turns out, and what we can learn this by doing simulations in the computer, that the mean of the sampling distribution of means, so this is confusing, it's a mean of means, is equal to the true population mean from our population. So if we know that our population mean, if mu is equal to 170 centimeters, then that means when we do this random sampling of 59 individuals and we do it 10,000 times and we get this sampling distribution of means, the most likely value that we will get is to be equal to mu, the population mean. But we can also get, we also now understand we could get a result out here, or a result out here, or a result here. All of these are possibilities, and they're going to occur with a probability that's defined by this sampling distribution. Okay. And this isn't something, this is something I'm going to tell you now, and maybe by the end of the course, it's going to make sense. But this population distribution, this distribution of sampling means that we have now, it also has a variance or a standard deviation here. And this standard deviation, this is what the sampling distribution, this is what this standard error is an estimate of, is an estimate of how much variation there is in this sampling distribution of means. So Tanya is asking, what if we don't know the true population mean? So that's right. We don't know the true population mean. We also don't know the mean of the sampling distribution of means, but they're equal to each other. So that's just the uncertainty that you have to live with, that you don't know them, but they exist. So I'm sorry to tell you that. But we can know them in the computer, and that's the beauty of the computer. Okay, so let's go and see. I'll show you an example of that. And Miles was asking, you're talking about the population mean is a constant and the sample mean is a variable. Does that affect the degrees of freedom? Why the population and sample variance formulas are so different? The degrees of freedom are, it's the same for the population. If we measured all 21,638 individuals in the NYU student population and computed the variance, the denominator would be still be n-1, so we'd still have to we've still lost that 1 degree of freedom. So the ability to estimate the or the formula for the variance isn't going to change in that case. All right, let me. All right, so here I'm going to simulate this in R, and I've put the R code up here so you can see how I've done this. Okay, so I'm going to make a population of 21,638 individuals in my computer. And so to do that, all I'm going to do is use a function that's called random normal. So make a random normal population. of 21,638 individuals that has an average height of 170 centimeters and a standard deviation of 10 centimeters. And that's what I've done here. And then I'm just going to plot it. And this is exactly what it would look like if we went out and did this crazy experiment and measured all these individuals. But this is much easier. I've just used one neuron to be able to do this. It's a much easier work, okay? And so you can see it has exactly the properties that we talked about. It has some very short outliers, some very tall outliers. People tend to be around the average height, but there's some variation, and that variation is quantified by the standard deviation. Now, and here, because we have absolute total information, we know that the mean of this population is 170 centimeters, and we know that the standard deviation is 10 centimeters. And now we want to simulate the process of sampling from that population. And we can do that very easily in the computer. This is much easier than if we had to do this in real life. We can just randomly take 17 of these individuals with probability defined by this distribution. We're going to sample those individuals. And then we can calculate the mean, the sample mean, okay? So here's my frequency distribution of those individuals. So we have one individual here, one individual here. These are the heights. And now I'm going to plot on here the mean. And so here's the sample mean in this case. So now my sample mean is 170.5696. I'm pretty lucky, right? The population mean I know because I have total information is 170 centimeters. I've just happened to take a sample and get a sample mean that's very close to it. But let's do this again. Let's throw those people back into the population and take another random 17 individuals. Am I going to get 170.5696 the second time I do it? Yes or no? Just a head shake will do.
Unlikely.
Unlikely, yeah. Not impossible, but unlikely. So let's do it again. We can just do that. So now here's my distribution when I take a different sample of individuals, 17 again, and here's the mean. And now the mean's 174.6 of my sample. I can do that again, take a third one, and now my mean is 167. So you can see I just keep randomly sampling from this population, compute the mean, 17 individuals every time, and I get a different sample mean every time. And so I am simulating this crazy experiment of continuously randomly sampling from the population with the same sample size. And when I do that, by doing this process, I can see that that sample mean is a random variable. Okay, it's not a constant like the true population mean of 170 centimeters. It is a random variable that comes from the sampling distribution of the means. And in the computer, I can do that. And the way that I'm going to do that is I'm going to write a little piece of computer code here that you're going to learn ultimately how to write. And this is called a for loop because I want to do it 10,000 times. And the key thing here is that all I'm using is this function mean. And my variable is the sample that I'm currently interested in, the random sample I've just taken. And all I'm doing here is I've written some computer code that's going to allow me to do it again and again and again, so I can get ultimately this sampling distribution of means. So these are the mean heights that I would expect for a sample size of 17 if I took random samples of 17 individuals 10,000 times, and I can simulate that experiment in the computer, okay? I can compute the mean of that, and this is where I can see, it's actually equal to exactly, you can see it on your screen there, 170 centimeters, okay? So you're right, we can't in real life know that, but this is to show you the true, to show you the relationship between the population mean from which we're sampling and the mean of the sampling distribution of means. All right, now I want to ask, and I can study, well, what if I increase my sample size? If I increase my sample size, am I going to get a better estimate? Yes or no?
Yes.
I see some nodding heads up and down. Okay, we're sort of it makes sense. Our estimate should be better if we take a larger sample, right? And we can do exactly the same thing. We can do it again and again and again, and we can plot that distribution now. And now you can see that the distribution of the sampling distribution of means is much narrower. It still has a mean of 170, but the variance of that sampling distribution is less than we observe for 17 individuals. Look here, you can see it goes from 170 and it's spread all the way out here to 175, and there are values. It's possible to get a value of 178. But if we look now, when we take a larger sample size, we can see the probability of the different means that we would get from that sample, and we can see that that variation is much greatly reduced, and that reflects the greater certainty we have of capturing the true population mean. Okay, so today what have introduced you to is going beyond thinking about statistics as a way of being able to describe data. Today, the take-home message is that what we're trying to do with statistics is account for the uncertainty that's associated with taking a random sample from a population. And that's essential because in genetics, in medicine, we're always taking a random sample from a population. We need statistics in order to help us determine whether the results of our sample are expected under a given model, or whether we should be surprised by the results that we see. And that's what we're going to be covering in this course. All right, so I'm going to stop here and